Hello, guys. So today we'll be discussing a very interesting problem statement, system design of your own in-house matrices monitoring system. So when we are saying like matrices monitoring system, there are multiple options that are available currently in the market. If have to say, for example, there are things like Dynatrace, then there are things like Datadog, New Relic, and there are plethora of tools. Okay, and even tools like the CloudWatch, Amazon CloudWatch, or AWS, Amazon CloudWatch on the AWS side, and the and Azure side, Azure Monitor. Those things also will come into the same thing. Of course, there are some extra features, some limitations are there on each of the tool, but overall, whenever we are thinking of this matrices monitoring tool, these are the on a very high level, you can think of this as the de facto tools in the market. Now, suppose why I chose this problem statement is the kind of approach, the kind of approach like we are going to take over there is like from scratch. If we have to build a system like this from scratch, building this particular system building this particular system will bring lot of details together. For example, we'll get to know like what are the kind of DB engine that powers this kind of system. We will also try to understand how we can group different kind of data, how we can query this kind of system, and how we can build our own visualizations, what goes behind the scene of this whole engine that we will get to know over here. Okay, so let's talk about like the system that we will try to design over here. So operational matrices when we are talking about. So operational matrices, when we are talking about the operational matrices, it comes like CPU load, uh, memory usage, and request count on the API side, or maybe like some internal APIs, external APIs, it can be anything like this. So on a huge infrastructure, if we want to track all of these things in detail, how exactly we are going to design our whole system, that is a primary motivation of this video. Now let's think about like what exactly is the scale that we will be looking at. If we at all if we at all have to even start designing this system, we need to have some idea about the scale. Otherwise, like in a very small scale, anybody can design it as a console application or a simple worker process as well, right? So suppose there are like 100 million DAU or daily active users. There are like 1,000 server pools, and there are like 100 machine per server pool. And also the retention of the data, like for example 7 day, there is a 7 day retention of data, and from 7 day probably on a 30 day plus data we will move into some kind of archival, because hardly we actually look into the system for 30 day plus data on a historical purpose. And of course there will be archival storage, but we will not give user immediate access. Maybe this is just to make sure that a system runs in a certain way. Okay, so this is on a very high level. The problem that we are going to solve is like in 100 million, for 100 million daily active users in 1,000 server pools and 1,000 machine per server, 100 machine per server pool, with a 7 day retention and 30 day plus archival. What kind of system we are going to have with CPU load, memory usage, and request count counters. So let's start by understanding the core components of the system. Okay, so what would be like if I have to just start designing this system on a very high level. So at first, all this operational matrices that I am having, this CPU load or mem usage. Okay, all these things will be ideally coming from some kind of a machines, right? So all the machines that we will be having. So uh, I can just keep on copying machine one by one. So suppose this is one of the machine. Okay, and similarly, like I'm going to have 100, 200, whatever number of machines. I'm just drawing two for the time being. So what will happen at a very first level is all these matrices, all this matrices data, all this matrices data will come and will get collected somewhere. Okay, so this is basically some kind of a data collector, some kind of a data collector, and this part like the data transmission. These two things will be the important uh, most important component on this. And what this data collector and the data transmission together will do, they will store it in some kind of a data storage. Okay, and once this data storage is being done, what we are going to do is, like in this kind of tools, we are going to have our own visualization. So visualizations like graphs or some grouping of data in a certain way. So that is why this data transmission, data collector, and visualization, these three things, probably we can think of a probably we can think these things as our core component, like the data transmission, the data collector, and the visualization of or the graphs. So now why data collection is so critical over here? Since there are so many machines are there, like there are since so many machines are there, like the data collection becomes of utmost important without overloading the network. So this many number of machines are there, and there will be a certain network associated with my data storage, right? So always we have to make sure that we are not exactly overwhelming our data storage and the network per se. So that will be one of the main challenge of this. So since there are so many machines, the collecting of data could be of utmost important. So what exactly the strategies we can take at the time of the data collection? So let's talk about this data collection with a little bit more detail. So when this data collection uh, is going to happen from our machine, how it is going to happen? It is going to happen in a periodic collection, or it is going to be like a complete constant flow on every millisecond or microsecond. So how often how often we are going to hold that data? So or for every second we are going to do, or 10 seconds, or every minute, the frequency will be very important. So here the matrices that we are aiming for is like CPU load. Okay, so CPU load will change probably like maybe every 5 seconds, how exactly the CPU loads are. And of course, the spikes will be reported. So I'm not considering the sudden spikes for the time being, but let's take it for a 5 second. If I am talking about the disk space memory, uh, we don't really care for what is happening in the every second. So maybe a 60 second or even 120 second will be fine. Like mm, how much your disk will get bombarded in every 5 seconds or 10 seconds delay, not much, right? And of course, like i- in case of extreme spike, probably some other phenomena we have to take care. But for the timing, let's 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 concentrate on these numbers, right? So um, now tailoring the collection frequency of this metric type will be very crucial, right? That we understood. Now let's talk about our data transmission. So now when we are talking about data transmission, what will happen in this case? How do you think this data transmission will happen? Like we are going to have our machines, and from these machines, we are going to send this data to probably like our storage servers, right? To our storage. So how this transmission will happen? What component will come in place? So one of the first thing, like in case you have seen the previous video of my system design series, that is where we have designed Kafka. So one of the best use case of Kafka is this kind of scenario where we are having a steady data flow and like very high frequency data flow, and some way we need some sort of a mechanism to control it. So Kafka or any kind of streaming queue is very useful in this case. So it can handle, why Kafka? Because it can handle very high volume of data and high throughput. High throughput, when I say, like it is it is mostly I'm talking about the frequency of the data, maybe um, 1 million data per second, something like that. Even Kafka can handle something like this. Okay, so and moreover, it makes the system very much reliable over here. The moment Kafka comes into the picture, because just think, if I expose some kind of a post API, okay, how difficult would be to get 1 million data per seconds? How good or how well my whole infrastructure has to scale with every single spike. So in to control that thing, Kafka is one of the best way. And if some matrices aren't transmitted properly, we might miss very critical alerts. For instance, if CPU uses spikes but the data never reaches the system, we won't even know until it's too late. So this kind of reliability will be very important in this aspect. Now let's talk about what kind of data storage will go behind the scene. So data storage, like are we going to use something like, so my first question or my first doubt that will come into my mind, that are we going to do something like SQL or RDBMS? So just give yourself a little bit of thought around this. Why or in what cases SQL or RDBMS are actually useful? So if we see over here, so SQL and RDBMS are good for um, high read data frequency. Like if I high read data load, like if I keep on selecting from our database, then it is very good. But uh, internally, RDBMS is basically a B plus tree, right? So every time we write something there, that B plus tree has to be balanced. So because of this internal reason, it is uh, not very apt for uh, high write load. So suppose I am writing something like 1 million data per second. Our SQL, how often that internal B plus tree will have to change. So in that case, it is not very good implementation. So what sort of implementations are actually preferred in this kind of scenario, where I need very high read and very high write guarantees? So I'm going to need over here some sort of a NoSQL, and for our use case the best thing will be time series. time series NoSQL databases. Now let's dig a little deeper onto this. Okay, so time series database are designed for fast writes and efficient queries and efficient querying over large data set. Whereas SQL databases, like querying millions of rows, again might become slow in compared to our time series database. So that is on a very high level what we are going to have. But like, what are the details of this time series database? We will definitely dig deeper into it in some point of time. Okay, so now let's talk about something like our data retention. Like we have been thinking about that we are going to retain the data for 7 days for immediate retrieval, and after 30 days probably we will go into the uh, archival. So that is pretty much a solid approach, but what we will do, like what are the storage engine or how the compaction of the data retention will happen, that 7 day plus 30-day archival, we will cover that thing in extreme detail. Okay, so probably like some kind of a schedule job we can do, and some kind of a data aggregation we will do. For that we need to understand our use case a little deeper as well. So we will discuss about those things in a later point of time. Now suppose we are now storing the data, we are retaining the data, and retries and the monitoring of that aggregation pipeline itself will be very necessary, very essential. Why? Because of the alerting. So what will happen when a CPU usage, there will be some kind of a thing like some parameters we are going to set. Suppose the CPU usage is going to be more than 90%, then we are going to have some rules or the static thresholds, and what it is going to do is based on those aggregations we are going to send our emails. Okay, so this is like there can be two things. One is like static or dynamic. So maybe a immediate CPU usage sometimes might not be a very good data, but what we can do is we can keep a certain kind of monitor that CPU usage over last 60 seconds in some aggregation mode. On last 60 seconds, if it is going beyond 90%, then we are going to send emails or we are going to send alerts. And so there can be like dynamic and the static threshold based on the historical trends. For example, we can even do machine learning to predict the normal behavior and the flag deviations, and multiple like the new age monitoring tools like Dynatrace, New Relic, or even the Amazon CloudWatch. They have some sort of a machine learning inbuilt into them to understand the behavior of the system in a dynamic way. So static is like a CPU usage getting some idea for last 60 seconds maybe, and dynamic is you kind of optimize your system based on the machine learning algorithms that you have. And then the visualization is again one of the more important part. So visualization is going to help, like the business, and end of the day, other than the engineers, nobody would go into the detail of those data, of those logs, and see what exactly is the trend is happening on raw text form. So rather, for the businesses, the visualization is very important. It will help engineers to spot patterns, and it helps business to see some sort of a graph. Suppose we are going to need a increased infrastructure, and we are making a case to the business that the infrastructure needs to be increased and this much amount of cost needs to be allocated to us. So business can go to the visualization dashboard and see the data. So dashboards are very good for making the quick decision making. And to just wrap up, yeah, let's discuss the basic building blocks of the system. the basic building blocks of the system, that we have to collect the matrices very efficiently. So at first, this data transmission or the at first the data collection, sorry, not the data transmission, at first the data collection will come in play. Then we transmit the data reliability into the tools like Kafka. Next, we are going to store it in a time series database and apply the data retention policy with scheduled aggregation job. Like suppose after 30 days we run some kind of a aggregation. After that, we analyze the data with anomalies and send multiple channels. It can be static or dynamic, both of these things. So so far we have done a good job in breaking down this complex system into some step-by-step things. So now let's discuss about couple of things that when we started about the started talking about the scale, what do we mean by this 100 million DAU, 1000 server pools, etc. Okay, so let's break down it with a real world analogy. Imagine you are working in a large e-commerce company like Amazon or Walmart, and they have massive server infrastructure to handle millions of users shopping online simultaneously. So how their server might be organized? Just if you could think, the best would be they would the best ideal infrastructure would be then they might need to group their servers based on the functionality, like grouping of the server. When I say this server pools, grouping of the server will be something like one for user login and user session, another is for payment processing, another is for order process. So they can have different systems like this. Now this groups are being called as server pools. Okay, so there can be like web server pools to handle the incoming HTTP request from users, like from bunch of users. There can be database server pools like manage database queries and storage. There can be cache server pools to frequently store to store the frequently accessed data and in memory for fast retrieval. So now let's say there a company has like 1000 server pools, right? A company has like this 1000 server pools that we are talking about, and within each pool, like there will be individual machines. These machines uh, can handle significant amount of traffic or workload independently. Like for order processing, suppose like these server pools are there are 100 machines only for order processing for a suppose for Bangalore or for Hyderabad or for the bigger cities. In this way, like thousands into 100, probably there will be like 100,000 machines will be present there. So if a machine in a pool, why this machine pool or server pool is required? So that might be your next question, like why we are going to need, why pools are required. So why pools are required? The basic idea is, suppose if a certain pool goes down, at that point of time the other or the replica pools can actually serve the traffic. And this is one of this replication concept or concept related to the consistent hashing, how exactly the server pools are uh, can handle a certain failure or can scale by themselves. All those things are I'd say one of the very basic things of building the system. So in case you are getting confused on this part, like what exactly will happen if a single machine goes down in this server pool, so I would request you to just go through few of the things on the system design basic block, like consistent hashing or how do we handle replication. Those kind of things, a simple Google search or going through the LLM would help you a lot. Okay, so basically this gives us redundancy, and redundancy ensures high availability. So how to design highly available system? If you just uh, do go to ChatGPT or any other LLM, and it will give you this all the behind the scene idea around it. Now imagine monitoring all these machines, right? Now where our matrices monitoring system comes into play. It needs to collect from the data from the all 100,000 machine efficiently, right? So now let's talk about like one of the things that we haven't talked earlier is the data retention policies. So we just touched the surface, so let's discuss a little bit more on that. Okay, so what do you think happens when we store raw data for 7 days or roll up to a 1 minute resolution for 30 days, further roll up to a 1 hour resolution for 1 year? So when we say roll up means I will aggregate 1 minute data and store instead of each second data. Suppose there are some user impressions like not user click impressions, rather where exactly a user mouse cursor is, that kind of details are coming through in a huge in a the, in a huge throughput traffic. So what exactly happen in that case? Like, is every single second or millisecond is important? I guess no. What you will find out is, like, if I keep on aggregating the data, I will be able to draw a certain pattern that okay, in last 1 minute the user's mouse was hovering around this place, so that will be enough for me if we can just let the outliers go. Okay, so now why we are doing these things now, why this aggregation, like there will be a 1 minute and later this 1 minute data maybe after a year will be clubbed to 1 day, and maybe after like 2 years it will be clubbed to 30 days. So in this way we can simply go ahead. So I think you get the idea that how exactly the data retention happens, and what is the very basic core principle behind it, like why we are doing it to save some space. As simple as that, because we know going forward after 1 year user might not be interested what happened to in his CPU 1 year back on a certain point of time. This is not going to be a very important data, so we can club that data into probably a whole month's data. We can aggregate it and store it somewhere. So suppose you are monitoring this CPU usage for every seconds, right? So the amount of data point it will store, it will certainly in long term will overwhelm any kind of storage system we take. So 1 minute resolution, 1 hour resolution, all these things will be very very useful over here. Now let's talk about one of the thing that we just touched on the surface, that is how we are going to handle the data in Kafka. So we mentioned earlier that collecting CPU load every few seconds makes sense because like the sudden spikes do matter, right? Whereas the disk space can be collected less frequently. So how Kafka is going to how Kafka is going to handle this data. So how often it will collect the data. So can we can we control it in some of the principles of Kafka? Yes, we can. One of the very basic principle of Kafka is batching. So several platforms like Kafka, RabbitMQ, Apache Pulsar, they allow the buffering events until a batch size is reached or a time interval elapses. So what can we do is, so these machines are here, right? So in machines we can run our own agents. So what exactly agents are? These agents are like small programs that we are going to run in our machines, and what these agents that are going to do is, like, it is going to collect the data every 5 seconds or every 10 seconds based on our requirement, and these agents will work as a producer. So this what these agents will do is, this agent will be, let me write it here, these agents are nothing but our producers. So producer means this is going to produce our data. This is going to produce our data and send it to Kafka. So these agents are going to send the collected matrices to the different Kafka topics. Again, in case you have some confusion regarding the Kafka topics or the partitions, please go to the previous video I say. So what exactly will happen is this agents will send data to a specific Kafka topic. So Kafka will have different topics. Suppose for CPU matrices, okay, CPU matrices there is one topic. Memory usage there is another topic. So this separate topic will receive the data. Now what we will do further optimization at our end is Kafka will hold the data. Kafka will hold the data. I will write it in this side for more clarity. Kafka will hold the data till the batch size of certain MB or time window. So suppose Kafka again holding the data for like 1 minute time or 30 seconds time, and then flush that data to your storage. Okay, so how the data will be again flushed? So there comes another concept called consumers. So Kafka cannot directly send the data to the storage. So our consumers will come in play. So consumers are nothing but worker processes that read data from these topics, and this process the data and forward it to the storage system. So why do you think like this separate topics are required here? What we were talking earlier, like CPU matrices and the meme usage, because it will allow us to have different workers in a different to have them work in a different frequency. For example, our CPU data may be the most urgent data, so we can process it faster using our consumers or the worker process. So this separate topics enables us to scale differently for each matrices. Like I can have a completely different scaling infrastructure for my CPU usage matrices, whereas a different scaling infrastructure for disk usages. So fewer worker might be suffice for the disk matrices only. And additionally, Kafka ensures the reliability. It will also make sure that everything is persisted on a certain time window, so it is not at all it is not at all missed. No data will at any point of time will be missed. Okay, so let's start by understanding the problem a little better. So uh, now let's start by understanding the problem a little better in terms of the data. Okay, so when we are thinking about the time series data, okay, so what exactly is a time series data? Okay, so as evident from the name itself, it has a timestamp, and for that timestamp it registers some kind of a events. So it will have a timestamp, and it is there will be a array of events rather, not a single events. So this is a very high level data structure. If I have to just write it what exactly a time series data is. Now why do you think the storing and querying time series data might be challenging at scale? So imagine we are dealing with this millions of matrices being written every day. Okay, so in case of like millions or billions of data per day, data point rather I would say data point per day, how the system would behave. Okay, so if there is a lot of data coming consistently, writing all those matrices quickly could be very hard. So we as we need to have a separate query for matrices to analyze trends, and that might take a long time if the database isn't optimized for querying properly, right? So this is a this is a write heavy as well as it has to be read optimized. Like I have to optimize the reading by some means. So in that case, the MySQL or any kind of RDBMS will struggle. So relational database are not designed for constant writes. They are more focused on getting a data structure and maintaining their transaction integrity, like the ACID principles. So let's think about what happens when you insert millions of rows into a relational database. Okay, so in a RDBMS, suppose I am going to insert millions of data, like when I am doing a insert into query. So I am having a RDBMS, suppose. What it will do is, like as we were discussing, like RDBMS is powered by B plus tree, and every time the B plus tree needs to be balanced. Okay, so on that, like 100 millions or 1 million inserts, our database will the indexing and the database base and the B plus tree balancing would be really really slow. Every time we add new data, the database has to update its indexes, and it will the things will go haywire. And if we have a lot of tags, label, and like different indexes, composite keys, and etc., so it will completely start breaking at that point of time. Like databases will be RDBMS will be brittle in that case. So indexes are essential for fast reads. So for fast reads, definitely I have to maintain the indexes. Now if I have to maintain the indexes, then like the heavy write and heavy read, both of these things fails simultaneously, right? So if we are talking about like the NoSQL now, how much time, like how much important is to have a schema for me here? I don't need any schema. The basic things that I'm going to need is I'm going to need a timestamp and an event, and there is no other relationship. There is no relationship other than this. I'm going to have some event tags. Like every events, like there are tag of events like CPU usage or API error. Other than that, this data is quite flat, right? So how much effort would it take to design schema for a time series database? Suppose in Cassandra. Okay, I guess we just have to figure out how to partition that data efficiently, how to put it into a different levels or different tags like CPU usage, API errors, disk usage, those kind of things. That's all right. And so in that case, this time series databases are best because InfluxDB or Prometheus. Okay, so there are a lot of time series databases are there. Cassandra like was made very popular by uh, mm, Discord. But later anyway, Discord moved to ScyllaDB. That's a different discussion. But InfluxDB, or there are Prometheus. Okay, Prometheus, it has become one of the de facto standards right now. InfluxDB, Prometheus, they are built specifically for time series data. These databases are optimized for high write throughput and fast queries. They don't really guarantees those gives you those ACID properties and stuff, but they gives you very high throughput and very fast queries, very fast query facilities. Okay, so InfluxDB again uses some kind of a in-memory cache, and it build indexes on those tags. So CPU usage, API error, there will be indexes around this also. So this feature helps a lot because the tag indexes make it faster to filter the data by labels, and that seems useful for visualization and alerts. Now let's talk about these labels or tags. Why it is important to keep the cardinality of the tags low? What happens if tag has too many unique values? Like we cannot have too many tags. Okay, like only CPU usage, API error. We cannot have like 1 million tags. Why? We need to have different a low cardinality or a low data distribution among the tags. This is one of the food for thought I want to give you. While designing this time series data, you can look into that. Okay, so now let's think more in more detail. Suppose we want something like a 10 million matrices. Okay, so the 10 million data, so the 10 million data, how is it going to actually get stored in our InfluxDB? Suppose. Okay, so InfluxDB already gives you tags and the fields to store those time series data, and the tags are basically key value pairs that are indexed. So while fields are basically the raw data. So why do you think the tags are important? Suppose you are monitoring CPU usage over 10,000 servers. Without tag, those 10,000 separate time series entries for CPU usage, how can we group? But with tag, definitely, like suppose it is coming from a certain group of machines, we can tag them in terms of the CPU usage. Otherwise I don't even know that this thing belongs to the CPU usage, right? So how exactly this thing looks like, I will just try to give you an example. Okay, so yeah, the data got little messed up when I copy pasted it. So but still I will try to explain over here. So you see the timestamp is the first thing. So timestamp here, timestamp here. Okay, so what is the measurement that I'm looking at? I'm looking for the measurement of CPU usage. What is the field? That is a CPU load. And what I have is CPU load as 85. What is the tag? Tag is the server ID. And what is the value of the tag? The server ID is 1. So what are the information I get to know? That on this given timestamp of this 2023 1001, the CPU usage of my server ID 1 is 85. And also, like if we are making it as a like a region specific services, the region is another important parameter as well. So that is what we need, this server ID and region here as well. Now the tags, we understand that it allows us to do a efficient query and aggregation of data. So this server ID 1, suppose like as a customer of your service, I own that server ID. So I can just query my server ID and get all the CPU usage related details or disk memory related details for from there. So how would it look like if I have to just convert it in terms of SQL? Again, it is not going to be SQL, but just for visualization, because everybody is quite aware of SQL. So select mean CPU load from CPU usage, where region equal to ist and time equal to -1 hour, that is in last 1 hour. How what exactly is the data in a grouping of 1 minute I'm going to have? So in this way, very easily I can group all the data. But again, different monitoring system has evolved to have their own querying system. Like if you have used Azure, in Azure they have something like KQL or Kusto query language. So it is like not exactly similar to SQL, but you can write your own NoSQL queries in a very structured way to get this kind of various kind of aggregation and stuff. So now we understand this tags help us organize and query the data more efficiently. But what if we have too many unique tags or values? Wouldn't that slow slow things down? Yes. High cardinality, having too many unique tag values, can indeed slow things down and queries and increases our storage requirement. For example, if every server had a unique server ID, we end up having a huge number of unique time series entries. Okay. To avoid this, we should keep the cardinality low. For example, instead of having server ID, we might just use region or some kind of a thing like a environment. So the cardinality or the differences among this uh, the tag, we have to we have to make sure that it is minimal unless it is explicitly required, like having 100 million server is not a good practice at all, right? So let's talk about this low cardinality tags a little bit. Suppose we want to monitor memory usage across different environment, production, staging, testing, etc. We can use the tags to group it, and it might come something like this to us. So you see over here the timestamp. Again, if I go here, the timestamp is here, the memory usage is our measurement, and what is the memory usage we are having, that is 70, and the tag is environment equal to production. Okay, now if we want to compare memory usage between production and the staging environment, we can easily query the data using that environment tag, that's all. And I think that makes sense. So we should use tags to have small number of unique values to keep the system efficient. So in our use case, we will have tags like region, environment, and the service to group our matrices. Okay. So what will be our basic schema? Now this can be our basic measurement and the schema. I will just copy paste it. Our basic measurement would be CPU usage, memory usage, and the request count. For the time being, we are having server ID, region, environment, and the service. Service means like what exactly the service account or the service, for which service this CPU is being used for, and the field will be like CPU load, the memory usage, and the request count. The exact the measurement is going to be the fields. Okay, so that is going to be my very basic schema. So by using this tag, we can actually efficiently aggregate and analyze the data and ensuring our system scale. So now this is like we are going to conclude our this first part of the video on this. And so what we have learned is, so there will be like hundreds and uh, thousands of machines, maybe 100,000 machines will be there. And what we are going to have is, we are going to have some kind of a agent running there. Those agents, what they are going to do is, they are going to send the data to our Kafka queue. Okay, so this is going to be our Kafka queue. This is going to be our Kafka. They're going to send data to our Kafka queue, and from here there will be multiple consumers. So in, I must mention one more thing, like different Kafka topic for CPU, for disk, for request count. Okay, and this consumers will take the data, and they will also have the facility to scale at their will. And once they take all the data, what they are going to do is, they are going to put it into our database. So our database that we thought is kind of an InfluxDB database, and there with different tags we are going to store our data. So InfluxDB, and over here what will happen is also some kind of a aggregation will run, some kind of a aggregation will run, and over the time, and it will keep on changing the data. So after the aggregation, we are going to again store in our data and in InfluxDB only, and from InfluxDB we are going to have our charts and visualization. So we are going to have a charts and visualization. So that is on a very high level. I draw this diagram, but like we gone into a good detail, like to understand each of this reasoning behind the system, like why Kafka, why we are going to have InfluxDB instead of RDBMS, why the aggregation is required. So all those details we tried to get into there. So this is the conclusion of the first part of the video, and in the second part we will again go further down into the system to understand a lot of things like many of the real world use cases, and how the visualization, how the aggregation, that everything will be done behind the scenes. All those details we will deep dive. Again, thank you very much for making till this part. I will come back soon with the second part, and second part will be definitely a way shorter than this. Thank you so much.